I was going to do another practice problem with phi-phi modeling in vapor-liquid equilibrium, but in the interest of time, I realized the semester is drawing to a close, and we still have a number of other topics that I wanted to get to. The next topic that I wanted to discuss is actually pretty interesting to me. It's something else that we cover in separation, so it's something that I wanted to make sure was not rushed. That is the topic of liquid-liquid equilibrium. So just like vapor-liquid equilibrium, you can have equilibrium in which you have two liquid phases as well. What does that look like? I'm willing to bet that in your refrigerator, you have a bottle of salad dressing. And if you let that salad dressing, so this will be not like a ranch dressing, but like a vinaigrette type dressing. If you let that dressing sit in your refrigerator over a while, you'll have a vinegar phase or a water phase. So this would be your polar phase. And you'd have the oil sitting on top, the non-polar phase. This is just one example of what liquid-liquid equilibrium looks like. So two liquids in a bottle. So if you take this bottle out and you shake it up, you can get them to mix, but there's still two distinct phases, as evidenced by if you let it sit for long enough, they separate into two phases. So two liquid phases. And because there are two phases, one of them will usually be more or less dense than the other. So denser one is always on the bottom. Just like in vapor-liquid equilibrium, we always envision the vapor phase being on top of the liquid phase because obviously the liquid phase is always more dense than the vapor phase. On bottom, and for example, this is a bottle of salad dressing. So as I mentioned, liquid-liquid extraction is of particular interest to chemical engineers because we can use it as the basis of a separation technique called liquid-liquid extraction. You may have seen this in your organic chemistry lab, but in case you haven't, and in order to give us some more context, I found a really cool YouTube video that I'd like to show now that does a great job of demonstrating how liquid-liquid extraction works. So this is called a short liquid-liquid extraction demonstration.
Everyone's about that time of year when we do liquid extractions in the lab, so I'm going to show you a short demonstration here and try to do a bit of a contrived separation, but one that shows you the technique, principles behind liquid extraction. Conductor extraction, I'm going to bring the hot plate and lab jack back into the fume hood, and I'm going to try to purify some 2-naphthol, which when it's pure looks like this, kind of an orange-yellow colored solid. But I've contaminated some with this blue food dye, so you can see the contaminant. And here is the result. It's a beaker full of 2-naphthol, which isn't orange at all. It's got sort of a greenish hue because that blue food dye is mixed in with the yellow naphthol. To clean it up, I'll be using two miscible liquids, N-butanol and water. And a few collection flasks. I'm going to use Erlenmeyer flasks for that purpose. I've also got my ground glass stopper and what's known as a separatory funnel. This is a pear-shaped funnel. It's tapered, and it's got a iron ring supporting it, so I can slip it in and out of that iron ring easily. Well, now that we've got everything together, we're ready to purify that 2-naphthol that I've contaminated. Now let's have a closer look at that separatory funnel. Well, the separatory funnel has a Teflon stopcock at the base. This allows us to remove liquids by draining them out of the funnel. It's secured with a nut and washer on the opposite side from the control. And we want to be careful with this Teflon stopcock because it's soft and it can be damaged. So I'll put it back in and I'll replace my washer, a little grommet in between there, and my nut, tightening it down hand tight so that I can still turn the stopcock, but it won't leak when I place liquids inside. Now notice that little opening there in the tapered portion of the stopcock. When it's pointed in there where we can see it, that means the stopcock is closed. So I'll leave it in the closed position and return it to the iron ring. Now let's begin the process of purifying this 2-naphthol that contains the blue food dye impurity. I'm going to put the beaker containing my impure naphthol on my stir plate, and to it I'm going to add my N-butanol. This is going to dissolve both the 2-naphthol and the blue food dye impurity. So I'll start my stir plate going, and in relatively short order I should see everything dissolve. Now you may think to yourself at first, what's the purpose of this? I'm just dissolving both the compound I want and the impurity. but that's the first step in conducting a liquid-liquid extraction. So at this point, you can see my yellow naphthol and my blue food dye have created a green solution. This is going to help me track where each one is as we go through my extraction. Excellent. Now, the next step in conducting my extraction is to be sure my separatory funnel stopcock is closed, because I don't want to make a mess. And I'm going to add that solution of my compound and impurity to the separatory funnel while it's resting inside of the iron ring. The next step in the process is to give my impurities somewhere else to go. So I'm going to give it 50 milliliters of water, a solvent in which the blue food dye is far more soluble than butanol, but the 2-naphthol is not. I'll gently pour that in, which isn't really a requirement of the procedure, but I'm hoping to show you the process as it happens, so I'm going to be very delicate with this as I go. Now you'll probably notice that once I've added that water, I haven't really changed much. I still have sort of a green solution of naphthol floating above water because the density of the butanol solvent is lower. Before long, we're going to take a step that ensures that we'll get all of that blue food dye into the water layer. What I'm going to do is take my ground glass stopper and secure the top of my separatory funnel so nothing can come out the top. And the reason I'm going to do this is that I have to agitate my mixture. By holding the top closed and inverting the funnel, I cause many, many small inclusions of one solvent to form inside of the other. This speeds the process known as partitioning, in which each compound dissolved in my original butanol solution gets a choice. Does it want to be in the water? Does it want to be in the butanol? After I give it a suitable agitation, I let it rest. And at this point, you can begin to see in this time lapse the two solvents separating from one another. After a period of time, you'll begin to see a change happening. Notice that I've got a thin layer of emulsion between the two. We'll deal with that later. But for now, you'll notice that I have a blue layer underneath of a yellow layer where I used to have a green solution. Now I'm going to remove that ground glass stopper from the top of my separatory funnel so that liquid can flow out without there being a vacuum forming in the headspace. And placing a suitable collection vessel below, here I'm using an Erlenmeyer flask, I'll open my stopcock carefully and notice that the solution that drains out from below, of course, is the more dense water, which contains only the blue dye. I'll watch carefully, ensuring that just as that thin layer of emulsion in the middle reaches my stopcock, I close it. There it is. Having stopped the flow there, I now have an aqueous solution of pure blue food dye. Next, because I had a bit of emulsion in there from the agitation process, I'm going to separate that into a separate vessel, a little beaker that I've set aside. And finally, I'll collect my purified naphthol by adding a new clean collection vessel and opening the stopcock and allowing that solution to drain into that new collection flask. Notice again, we've got a yellow solution now. We've gotten rid of that blue impurity that was ultimately causing my product to look green. Using this process, we can separate a number of different organic compounds from one another. And of course, once they've been separated into different flasks in solution, we use a number of other techniques to finally recover the solid from these solutions. But for now, this ends our short demonstration of a liquid-liquid extraction. Thanks for watching, everyone. I'm Professor Davis from ChemSurvival.com and the YouTube channel ChemSurvival. See you next time.
So once again, the main idea, I hope you enjoyed that video, but liquid-liquid equilibrium is going to form the basis of our liquid-liquid extraction, which I just showed you a video from a chemistry lab. And chemical engineers use liquid-liquid extraction as well. Just in general, like most processes that we study in chemical engineering, scaled up greatly from what you'd see in a chemistry lab. So in a large column or something like that. The benefit of liquid-liquid extraction over distillation is that it does not require boiling and condensing. And because of that, it does not require as much energy as distillation. as much energy as distillation. However, it does have some drawbacks, and those drawbacks are a discussion for separations. Again, I'm just trying to give you a reason or a motivation for why we're studying this. So in phase, the first question that we could ask is, why does this even happen? Why does LLE even occur? It may seem like a bizarre question, but I mean, if you really think about it, we mix liquids all the time. So if you mix water and ethanol, for instance, it doesn't form two distinct mixtures. So it's actually very bizarre that sometimes you can have phase equilibrium in liquid phase itself. So the answer to why does liquid-liquid equilibrium occur is because, remember, the system wants to minimize the Gibbs free energy. System will spontaneously minimize G. We'll talk about that more on Friday of how you'd go about calculating the Gibbs free energy for liquid-liquid equilibrium. So before discussing more of those details of why, let's first learn how to read a phase diagram. So just like the TXY and the PXY diagrams, we have something similar for liquid-liquid extraction. So let's say we've got temperature on the y-axis, and just like a TXY diagram, it would be mole fraction on the x-axis of component 1. And we'll start with, so in separations, liquid-liquid extractions are all ternary systems, meaning there's 3 components, but we'll focus on just a binary system here. So 2 components such that we can draw this phase equilibrium diagram. And just like in the TXY diagram, we have some experimental data points which we can connect. And oftentimes, liquid-liquid extractions have this kind of parabola shape to them. So this is what we call the phase envelope. Outside of the envelope, we have the stable region. So this is all outside of the envelope. And in the stable region, there's only one phase that exists. Stable region is one liquid phase. But below the curve, we have what's called the unstable region, where 2 phases will result. So if your composition and your temperature is such that you are in the unstable region, just like in vapor-liquid equilibrium, so let's say our composition is here and our temperature is there. That means our coordinate is there, falling in the unstable region. If you're in the unstable region, you form 2 liquid phases, and the compositions are given by the tie line, just like it was in the TXY or PXY diagrams. 2 liquid phases form, and compositions given by a tie line. Given by tie line. So that tie line goes horizontally across, and where it intersects with the phase boundary, we call X1 of phase 1, and this would be X1 of phase 2. Where phase 1 and phase 2, you could label them however you want. You could say this is X1 of phase 1, this is X1 of phase 2. To my knowledge, there's not really a convention of which phase you call which. You just denote them with Roman numerals 1 and 2. So those are the basics. Well, one more thing I wanted to mention is oftentimes you'll see a black dot here. This stands for the UCST, the upper solution critical temperature. And you notice the shape of the diagram is such that if the temperature is above whatever this UCST is I guess more properly drawn on the y-axis, there is no liquid-liquid equilibrium that can form. So all compositions, all solutions are one phase above this UCST. The other thing I wanted to point out is that it is a function of composition as well. So for instance, if you have a temperature that is below the UCST, so let's do this in a different color now. So let's say this is T1, but my composition X1 is there. then my coordinate is there, that's just in the stable region, which is in the one-phase region. So just because the temperature is below the upper solution critical temperature doesn't necessarily mean that you'll have two liquid phases that form. That's all I wanted to say for the introduction to liquid-liquid equilibrium. On Friday, we'll come back and we'll talk more about why this occurs, getting more into the theory of liquid-liquid equilibrium.